Hello everyone, my name is Roshan. I am going to tell you about formation of methanol. So let us start. What is the content in this PPT? First of all, raw materials and quantity analysis, flow sheet and process description, unit operation, unit processes, mass balance, energy balance, major engineering problems and their solution. So let us start. First of all, I am going to tell you about some properties of methanol. So first, molecular weight of methanol is 32.07 gram per mole. Melting point is minus 97.8 degrees Celsius. Boiling point is 64.7 degrees Celsius. Solubility highly soluble in water. Also, methanol is highly toxic. There are two methods of methanol production. First one is catalytic hydrogenation of carbon monoxide, and second one is oxidation of LPG. So about raw materials. Raw materials include natural gas, coal, biomass, carbon monoxide, hydrogen gas, carbon dioxide, methane, water, air, oxygen, catalyst. About quantitative requirement, for 1 ton of methanol production, we required 0.127 ton of hydrogen gas, and about carbon monoxide, we need 0.89 ton of carbon monoxide. And plant capacity is 100 to 800 ton per day of methanol. So this is flow sheet and I am going to explain. First of all, our raw materials hydrogen and carbon monoxide in molar ratio of 2 raised to 25 raised to 1 compressed through a compressor at the pressure of 200 to 350 atm or 3000 to 500 psi pressure and fed to a highly pressure converter or a reactor. Then next step is a high pressure converter which is made by copper line steel where temperature is 300 to 375 degrees Celsius and pressure is about 3000 to 500 psi. The raw materials, which is carbon monoxide and hydrogen gas, sent to catalyst for the reaction, and their carbon monoxide and hydrogen gas react to each other to form methanol reaction. In the reactor, temperature is maintained. Also, the reactor exit gases are cooled by heat exchanger with reactants and with water. The unreacted exit gases are recycled or purged to maintain molar ratio. Liquid methanol is depressurized and purified by treating with potassium permanganate, which requirement is 0.1 to 0.5 kg to remove traces of ketones, aldehydes, and impurities. Then next sent to the ether tower, where removal of light and such as light compounds such as dimethyl ether and other compounds are removed. Then further sent to methanol tower where fractionator is used to separate methanol from high molecular weight compound like higher alcohols. And then we get uh, separated methanol and water and we get 90% yield of methanol. Here we can see there are heat exchanger such as condenser are used. About process description. What are the unit operations? First of all, mixing, heat exchanger, separation, distillation, and compression. These are unit operations. And unit processes. First, reaction happen in reactor, which is carbon monoxide is reacted uh, with hydrogen gas to form methanol. This is primary reaction. About mass balance. So 1 ton of methanol required 0.127 ton of hydrogen gas and 0.89 ton of carbon monoxide. For 100 kg of methanol production, we need 12.7 kg of hydrogen gas and 89 kg of carbon monoxide. And also, which yield is 97%. So you can see the yield is 98 kg of methanol using 12.7 kg of hydrogen gas and 89 kg of carbon monoxide, and 2% is unreacted hydrogen gas and carbon monoxide. So mass balance, molecular weight of carbon monoxide 28 gram kg per kilomole, and hydrogen gas is 2 kg per kilomole. And about methanol, it is 32 kg per kilomole. Using the first reaction, first in which 1 kilomole of carbon monoxide is reacted with 2 kilomole of hydrogen to give 1 kilomole of methanol. For it, 100 kg of methanol, which is 100 divided by 32, is equal to 3.125 kilomole of methanol is produced. Thus, the reactant required are first carbon monoxide is 3.12 multiplied by 1 kilomole is equal to 3.12 kilomole of carbon monoxide, and there are 2 kilomoles of hydrogen gas. So 3.125 multiplied by 2, we get 6.225 kilomole of hydrogen gas. So total H2 converted to kg is uh, carbon monoxide required is 87.5 kg we have calculated, and hydrogen gas is 12.5 kg. So the excess amount and the gas which is unreacted is 1.5 kg of carbon monoxide and 0.2 kg of hydrogen gas. So the first reaction gives 70% yield, which is 85%. We get uh, the 70% of 85 is 59.5 moles, and methanol produces 59.5 moles. H2 consume is 119 moles. In side reaction, 30% yield is we get 30% yield. 30% of 85 is 25.5 moles, in which methane gas is produced 25.5 moles, water is produced 25.5 moles, and H2 is consumed 76.5 moles. The total H2 consumed in overall reaction is 195.5 moles. The total heat release is minus 2845 kilocalorie. About major engineering problems. So the first major engineering problem we face is reactor design. As we know, the reaction is exothermy, in which heat is released, and the reaction is favorable at constant range temperature. So higher temperature causes catalyst damage and deactivation of catalyst, and also lower the methanol yield. So the solution on this is use multi-tubular reactor for internal cooling. This will reduce the cost and increase the yield of the reaction and yield of methanol. And the second major engineering problem is catalyst fouling. During the reaction, higher weight byproducts such as aldehydes ketones are produced. These stack into the catalyst surface and block active sites, which reduces the efficiency of catalyst and reduces the reaction rate. The solution on it is use catalysts need frequent requirement replacement and operate with excess hydrogen gas. And the third problem is inert gas accumulation. In the reaction, in the recycle gas loop, internal gas like nitrogen, argon, methane build up and they do not react over the dilute area with syngas. They accumulate in there. The solution on it is install a first line to remove part of the recycled gas streams and prevent inert gas buildup for it. Thank you. The reference is taken from Dryden's book and Google Scholar from research paper. Research paper. Thank you.